Good afternoon, everybody. So you can see here the metal oxide modified silicon carbide nanocomposite is the topic. And let me introduce my co-authors. You can see that Gopa Misra. Gopa Misra is now she was research scholar in our institute, and it is mostly her work I am going to present. And Dr. Parida was the man of catalyst, and I am Dr. SKC presenting this work. I am a metal scientist. So let me go to the topic first. So mostly I will be discussing about the silicon carbide nanocomposites, how it is prepared, what is the advantage of silicon carbide over the conventional catalyst support materials. So outlines of the topic is the advantages of silicon carbide as catalytic support material, then thermal plasma synthesis of silicon carbide from risers. Then we have different type metal oxides like titanium dioxide, sulfur dioxide, sulfur mediated TiO2, SiC, then WO3, BPO modified silicon carbide non-composites, then evaluation of catalytic activities, all the oxides, and finally conclusion. Okay, so mostly industrial chemical processes rely heavily on the catalysis, and so researchers are always on the lookout for alternate catalytic materials that may improve existing process or lead to new ones. This slide is moving. Hello? Is the slide is moving?
Yes, sir, it is.
Okay, no problem. So advantage of silicon carbide as a catalysis material. So majority of commercial catalyst, as you know, is supported on alumina, silica, zeolite, and carbon. What are the problems? Poor heat conductivity and chemical reactivity of alumina, silica, and zeolite. So that reacts with sometimes materials. Weak oxidation resistance of carbon, we know carbon cannot above 600 degrees, it gets oxidized. On the other hand, silicon carbide exhibits high thermal conductivity, is a very good thermal conductor, and high resistance toward oxidation. In fact, more below 1000, nothing will happen to this, 1000 degrees Celsius. Nothing will happen to silicon carbide. And high mechanical strength, it has got very good mechanical strength. Of course, it is one of the hardest material also. Low specific weight, is lightweight material, density is around 3.2. Chemical inertness, it is not attacked by neither acid nor alkali nor anything. So it is almost like very inert material. So these are the properties required for good heterogeneous catalyst support material. More so, this metal support stability and is higher, and metal support interaction is also lower. So that is why it is one of the best catalytic support material. How silicon carbide is produced commercially? You can see here one core is graphite core is there. Over that they put low sulfur petroleum coke, which is source of carbon, and they put high quality sand, which is source of silicon. Once silicon and carbon is packed together, they heat for a longer period, ohmic heating, and it may take several hours, maybe several days to produce the silicon carbide. You can see this how silicon carbide looks like. Hutchison furnace they produce large quantity. But on problem is here, you can see that this has got particles produce a large agglomerates with wide range of particle size. Not good for our purpose. So what is to be done? We have to prepare fine silicon carbide and maybe ultra fine silicon carbide nanosite. So one of the candidate material is risers. What is rice, particularly Asian countries, rice in the rice oil is available as a byproduct of rice milling. It is considered as agriculture waste. Particularly in the area of Delhi and other things, they burn quite a huge amount of husk, not only rice husk, there's other paddy husks. So that is why this environmental problem is a really serious issue there. So rice husk usually contains a high amount of ash, and practically it is mostly silica. So it is a good amount of high silica is there in a very high surface area silica. So also carbon is there available in the rice husk. So these risers which can be waste and it creates an environmental problem can be placed for making a good catalytic support material like silicon carbide. What is the advantage here? The risers get cheap but abundantly available, and this is almost waste. In risers, silicon and carbon are intimate in contact, thus no mixing is needed, as earlier I mentioned, silicon quartz and low sulfur petroleum coke has to mix together to make their reaction, because silicon and carbon has to be together to make this silicon carbide. Intimate contact of silicon and carbon in a very fine form, it is very fine form. You would say the reaction time considerable. If the particle size or initial particle size are very small, obviously your reaction time is reduced considerably. And the silica carbon rhesos are also many purer form. You can make it further pure by acid leaching initially the rhesos. So all the small amount of impurities are there that can be removed. So then you can produce almost like 99.9% silicon carbide, pure silicon. In fact, I have produced that. Since starting material silicon carbon rhesos is much finer form. So finally you expected that it is a final product will be also fine form. So which will be good for our purpose. So this was first done in USA, Lee and Cutler in University of Utah. They produced in 75 silica, and you can see that the reaction is like this: silica and in a very small fine form, and carbon is also in fine form, and this is the reaction silicon carbide to carbon monoxide. Probably in a novel approach, we produce fine and ultra fine silicon carbide from the isos using thermal plasma. Probably this is first of its kind in the world. Plasma produced silicon carbide is further utilized as nanofluids. We have used as a nanofluids, catalyst, composites, and recently this same silicon carbide can be utilized in magnetic materials. Before that, since we have used thermal plasma, let me introduce a little bit about thermal plasma. What is the plasma? Plasma is actually nothing but a collection of molecules, atoms, excited species, electrons, cations, ions. Basically, ionized gas is plasma. It says a solid. If you give some energy, it becomes liquid. If you give the energy, it further becomes gas. Either by heat or by some other energy, nuclear energy, you can convert it to like this. But if you, this is the three state of matter. If fourth state of matter, once you become further heat or further energy, it becomes ionized, and that is we call fourth state of matter. And you know the nature has made such a inverse of everything is almost like plasma. All this sun, stars, and even our nature, whatever you are seeing, all are plasma only. So nature more than 90% is plasma. How to distinguish between plasma? There is thermal plasma and non-thermal plasma. In most of the laboratories in IITs and many institutes, they use mostly cold plasma. You know, this sputtering type of things, that is cold plasma. Molecular PCVD, all this type of things are mostly used by cold plasma. See, what is the difference? Degree of ionization may not be 100%. In sun it is 100%, but our laboratory we do it less than 10%. So basically, once you get the ionized gas, we can control it. Pressure is almost like atmosphere, 1 atmosphere, and whereas the non-thermal plasma pressure is very low. So in the process, what we can achieve a very high temperature here, whereas non-thermal plasma is low temperature. You can see the next slide. You can see here. This is at the low pressure plasma. That means ions and electrons and ions are quite rare, and it is separated, well separated out. Whereas in thermal plasma, it is quite dense. That is why you can see the graph here. Here around this, here thermal plasma, here it is low temperature plasma. What is the use of this? Thermal plasma is used for, because since it's high temperature, it can be used for metallurgy, cutting, welding, and smelting. And you can see there, and of course, sintering of ceramics, waste treatment now is major player here, because you can make a syngas from any waste, and that waste can be utilized for making green hydrogen. That work is still progressing, so it will continue. Non-thermal plasma, you can do plasma assisted because of low temperature plasma. So it is surface treatment, mostly used for surface treatment, coating, diamond coating, thin films, all this type of things. Of course, you can see the fluorescent and your plasma display, etc. So let us concentrate on only thermal plasma, because we are working on thermal plasma. This is a cathode and this anode, the water cooled anode, the copper, and this is a thoriated tungsten. If you make an arc here, then plasma comes out like this. So this is difference is that if the arc is to be transferred to the work anode, so it becomes transferred arc, it is a non-transferred arc, standalone plasma. And here is the inductive coupled plasma where the electrodes are outside, copper electrodes. So gas is pumped here inside the plasma. So since electrodes are not contact with the plasma, we can produce a very pure material. You can see the temperature profile here. As I told you, non-transferred arc plasma efficiency can be 50% to 90%, but in the transferred arc plasma, the efficiency is more than 90%. That is why it is quite efficient. And you can see this temperature here. It's a core temperature is around 20,000 K. Okay, so even this what's saying this is almost room temperature. That means with a small volume we can generate a very high temperature. That is why the reaction can be very fast in the plasma. These are some of the pictures where I have worked. This is our extended plasma we have developed ourselves. This array plasma in Germany. This is some commercial. This I used in Germany. What is the advantage of thermal plasma methods? This high temperature plasma because you can 10 to the power 4 K induce fast reaction. Is the temperature high, reaction will be much faster. I told you that this is confined in a very small area, so that the particles comes out of that, it immediately quenched. So nanoparticle synthesis is also very. Then controlled environment, you can use any type of gas, argon, hydrogen, nitrogen, etc. And we have used all sorts of gas for different purposes. Suitable for low cost, high volume production because when a small reactor you can produce high volume materials. And with the continuous manner with computer process control. That means it is good with amenable to operation in a continuous manner with computer process control. Okay, so how we produce in our laboratory. This is the rhesus you can see here. If you take out the volatiles, it contains almost 60% volatiles. If you take out the volatiles, and this is treated in 550 degree nitrogen, you can see that silica becomes 49% now. Carbon is 47% because almost all the things are silica and carbon. In fact, the carbon is a little bit higher than the stoichiometric requirement of the carbon. So it is very good for making silicon carbide. Other impurities that you can see can be leached out with initial stages. So you can make a very pure carbon. So this is the possible reaction. You can see the thermodynamic equilibrium diagram, chemical equilibrium diagram. This is the type of reaction it occurs. Because silica and carbon, next silicon carbide, carbon monoxide comes out. And you can see that this range, around 1500 K to 3000 K, you can make a silicon carbide formation, and which is easily available in the plasma. So plasma processing can be very fast. What is the problem with rhesus? Why people have not? It has not been commercialized so far. Problem is that inefficient heating of rhesus in a thermal insulating material. The rhesus is a thermally insulating material. Mostly you put a furnace, give a heat from outside, it will not go to the rhesus easily because rhesus is a thermal insulator. So what we did? We did just reverse. You can see that plasma is formed inside and rhesus back outside. So which was bad material now become good material because now it's insulator. So once it's insulator, heat is retained, and since the plasma is produced inside, the heat transfer can be done. And since the plasma gas is going through this, so you know this carbon monoxide can be easily removed. And when silicon carbide starts forming, its arc work is in a transferred arc mode. That means efficiency is more than 90%. So in the process, you can see here, these are rhesus. I see a picture of rhesus. You can see that there is silica rich areas, and background is carbon. And within 5 minutes, almost I can put a half a kilo of rhesus. Within 5 minutes, you can see the formation of silicon carbide. See, by the time I am talking, I can produce silicon carbide. So easy and so fast. And 20 minutes, you can see that all the silicon carbide peaks are there. Of course, some unreacted stuff will be there. And that has to be removed by heat treatment with carbon, and the silica can be removed by HA or sodium hydroxide. But you can see the final product. Plasma processed product is like this, after the post processing, you can see the product like this. This is a 100 nanometer scale. You can see how small fine particles are. This is the real scenario. This is the real picture. This is how the graphite crucibles are there. So it is inexpensive, and packed with bubble alumina. This is a graphite core here, and you see the plasma how it is formed. It's a real picture what I have done in my work, and you can see the isocyclic pack here, and this we put a cover here to protect it, and you see the plasma in operation. After the plasma experiment, you can see that how it's. And we have all patented in Indian patents. 2 patents are there. This is for this work. Second one is for other reactor I made. In-flight processing directly you can put silicon carbide or isocyclic in the plasma, and instantaneously you can get the silicon carbide. That I am not going to present here. So what further we did? We did metal oxide modified silicon carbide. This is what the Gopa Misra has done. Did her PhD work. See that he did 4 type of things. One is silicon carbide to nanocomposites by Saroj method, and application towards rhodamine P degradation in presence of solar light. Further, he has put sulfur in this system, so that this hydrogen photocatalytic effect is more further enhanced. And again, same thing is produced with Saroj method, and it was used for water splitting reaction. Third one is tungsten oxide promoted silicon carbide by wetness impregation method, and towards esterification of reaction, and development of PPO, vanadium pentoxide, silicon carbide composite towards solvent-free oxidation, methanol, and formaldehyde. And then let's see the Gopa Misra, and you see all the papers are published in ACAC Omega recently. Then Dalton transaction, RSC advanced, and SEC social chemistry and engineering. So I cannot describe all the work, but I will a little bit tell about only one work. This beta silicon carbide to nanocomposite by Saroj method and its application towards rhodamine P degradation in presence of solar light. You can see that how it is prepared. Silicon carbide dispersed in ethanol. Then add some titanium isoprotoxide, drop by drop in this white stirring. Then hydrolysis and condensation reaction occurs with acetic acid and water. And further it was cleaned and dried. Then further calcined to form this beta silicon carbide. You can see some of the results here. These are the beta silicon carbide. This is anode, that is PiO2. And you can see that if we are loading different composition, we can what is the, and you can see this side. And these properties of synthesized nanomaterials like catalyst, different surface area increases, and so also pore size. Show the different pore size and pore volume. And you can see the most interesting thing is band gap. Band gap is around 2.2, and let's say this is it's reduced to, and it's, you know, PiO2 is 3.2. So by doing this, band gap is, see, this is gives the best result. That is why I'm showing this. Band gap is 2.54, which is very good for photocatalytic effect in visible light. That is why we do, because if you see the visible light, the 3.1 is around 700 EV, and 400 is 1.7 EV. So if you have a heterostructure, then the band gap is coming here, which is good for visual light. And you can see that structure here, TM image, and this is a TM image, and it is silicon carbide. And this is a silicon carbide, and it's almost, you can tell that's a core and cell structure. Core is silicon carbide, cell is here. You can see the mechanism photoexcited. So this electron is see this once you do the N type TiO2 and P type silicon carbide, what happens? Band bending is occurs. That is why this heterostructure forms. And see, if you shine here light here, what happens? The electrons are already here and holes are here. separated out because of the bend gap. That is why it is because Fermi level, to adjust the Fermi level, the bending occurs, and there is a p-type n-type, so that they push the electrons towards conduction band and force toward valence band. And you can see that because of that electron generation is occur, so rhodamine p degradation can occur. Rhodamine p picture. And you can see here efficiency around 20% to 8%, become 87%. Which is not bad. So conclusion, what we can find from this: silicon carbide TiO2 nanocomposites can be easily fabricated by solder process. Established p-type beta silicon carbide n-type TiO2 heterojunction has been confirmed by XRT XPS. We have done some. I have not shown all the results. We have done the FTR and all the studies also. Surface morphology interaction between beta silicon carbide TiO2 nanocomposites are well explained by TM and FS study. Separation of photogenerated charge carriers lead to enhanced photocatalytic activities. Narrow band gap silicon carbide extends spectral response to TiO2 from the UV to visible region, as I explained earlier. The obtained p-type silicon carbide and nano heterojunction nanocomposite can be useful candidate material for solar light driven photocatalysis for other applications also. So let me tell about other activities in our department, which I was heading earlier. Now you can see the fixed bed reactor. This is a moving bed reactor, that in-flight processing reactor. Directly you can put the materials and directly process the high temperature plasma. Here, moving bed reactor, continuous production is possible, and here just melting operations. So we produce also synthesis of nano-ceramic powders like silicon carbide, aluminum nitride, CNT, zinc oxide, manganese oxide, etc. Then we prepare also fused ceramics like molite, zirconia, protophone molite, stabilized zirconia, arsenide, galaxite, magnesium, etc. Then we also produce high value products from waste. As I told, we have produced already nano silicon carbide, palm then KC from narco plant sand, molite from fly ash, then composite ceramics powder, polyuricell waste, KC from red mud. These are some of the work, and we also produce carbide and nitrates directly from ores. So utilize these sand minerals, so that we have worked extensively. In fact, I am working on this as an emeritus scientist on this, making zircon dibride silicon carbide for zircon and FEL TSC from ilmenite. And this work has been done, going to patent receptor very quickly. And we have also plasma assisted sintering. This was some students that did PhD work on this. And we also prepared alloys and also processing gemstone, which can be processed within 1 minute. And recently, I am working on graphene, so I want to show you. This may be interested to some of you, because you can see this. This is a commercial one, which I got from India, from the institute. Commercial they are selling, the cost is pretty high. You can see this 50,000 Indian rupees. Where plasma we can produce, you can see the pronounced 2D peaks, where you can see no 2D peaks here, almost negligible. But in our case, you can see the pronounced 2D peaks, and you can see the graphene plates here. Graphite per year, and this is done from waste, and within 10 minutes. The time I am speaking, I can produce some graphene to you, and maybe 10-20 grams easily, no problem at all, and no chemical routes, nothing, purely physical route. I would like to thank those who have helped and supported me for this work, and thank you very much. You can see here, so what we could not do here in our work. See, this is, you can see this silicon is produced in plasma, and in surface itself you can modify it with hydrogen passivation. So similarly, if you produce the silicon carbide here, you can also put with a TiO2 or maybe some other oxide things. So directly you can produce the catalyst instead of going by making plasma methods and again doing chemical methods. But single method itself, it is possible to produce direct catalyst. I hope some of you can do this work. With all this thing, thank you very much for your kind attention. We hope that this thing work will be done.